So here we're going to look at some basic functions that we can take as starting points and look at variations of these functions later on to build them up into more complicated functions. So we'll be looking at functions like constant function, the identity function, the absolute value function, the square root function, the squaring function, the cubing function, things like that. So the simplest possible function you could have, I guess, would be a function that no matter what number you put into it, you always get the same thing out. So in this example, no matter what number we put in for x, we always get the same number, 1.3, for f of x. What's f of 0? 1.3. What's f of 1? 1.3. What's f of 2? 1.3. What's f of 17? 1.3. And so on. So this is a constant function. The value is always the same. It's constant no matter what you put in for the independent variable. And the graph of a function like that is just a horizontal line that goes right straight across, because every y-coordinate on that line is the same number no matter what the x-coordinate is. And then the second most simple function you could possibly have would be a function where no matter what you put in, you always get that exact same number out. So that function is the identity function. F of 1 is 1. F of 2 is 2. F of 9 is 9. F of -1 is -1. F of any number x is just that same number x. And the graph of that function is this straight diagonal line like this. So every point on this line has its y-coordinate and its x-coordinate the same. You got points 0, 0, and 1, 1, and 2, 2, and -1, -1, and so on. Now getting a little more interesting, we have the absolute value function, the function that gives you the absolute value of whatever number you put in. And that means if the number you put in is a positive number already, it just gives you that same number. But if the number you put in is a negative number, what it gives you is the opposite of that number, which is positive. So f of 1 is 1. F of -1 is 1, that is positive 1. F of 2 is 2. F of -2 is also 2. And f of 0 would be 0. So you can see all that on the graph. When x is a positive number, this just looks like that identity function that we were looking at. But if x is a negative number, the y-coordinate isn't down here negative, it's up here positive. So the graph has this V kind of shape with a sharp point, a turning point there at the origin. So the domain of the absolute value function is all real numbers. You can have the absolute value of any number, but the range is from 0 to infinity. The absolute value can come out to equal only a number that's greater than or equal to 0. So absolute value can never be negative. It can only be positive or, at lowest, 0. And the absolute value function is an even function. Remember, an even function is one where if you plug in a negative number, you get the same value as when you plug in the positive of that number. So the graph has this symmetry. It's symmetric with respect to the y-axis, just like even functions are. What about the square root function? So you put in a number, and what you get out is the square root of that number, the number that you have to square or multiply by itself to end up with that number. So if you plug in 0, you get the square root of 0, which is 0. You plug in 1, you get the square root of 1, which is 1. You plug in 2, you get the square root of 2, which is approximately 1.414. If you plug in 9, you get the square root of 9, which is 3, and so on. Now, if you try to plug in a negative number, it's undefined unless we want to get into imaginary numbers. And I said in this chapter we're just focusing on real numbers. Those are the only ones that show up on the graphs. So from that standpoint, the domain of this square root function is just from 0 on up. Just the non-negative numbers greater than or equal to 0. So we can take the square root of 0, we can take the square root of any positive number, but we can't have the square root of a negative number. X can't be negative. And the range of this function, what this comes out to be, is also greater than or equal to 0. So the number you put in has to be greater than or equal to 0, and the number you get out as the square root of that has to be greater than or equal to 0. By the way, notice this is an increasing function on this interval from 0 to infinity. The squaring function takes whatever number you give it and gives you that number squared. That is, that number times itself. So if you put in 2, f of 2 would be 2 squared, which is 4. You put in negative 2, f of negative 2 would be negative 2 squared, which is also 4. Remember, a negative times a negative comes out positive. F of 0 is 0 squared, which would be 0. F of 5 is 5 squared, which would be 25. The domain, the graph looks like this. It's a parabola shape with its turning point, its vertex at the origin. That's the lowest point on the graph. The domain is all real numbers, so you can put in anything you want for x. Any number can be squared. But the range is from 0 to infinity. What you get out of the function, the value of x squared, has to be greater than or equal to 0. It's never going to be negative. And you can see that on the graph. There are all possible x coordinates, but the y coordinates of the points that make up the graph are all greater than or equal to 0. And this is an even function. The cubing function, where you plug in a number and you get that number cubed, that is, that number to the third power, that number times itself again. So if you put in 0, you get 0 cubed. 0 times 0 times 0 is 0. You put in 2, you get 2 cubed. 2 times 2 times 2 is 8. You put in negative 2, you get negative 2 times negative 2 times negative 2, which comes out to be negative 8. Put in 5, you get 5 cubed. 5 times 5 times 5 is 125. And you can put in any number you want. The domain is all real numbers. And you can get out any number you want. The range is all real numbers. So x cubed could turn out to have any real value. And this is an odd function. Notice how f of negative 2 is the negative or the opposite of what f of positive 2 is. And the graph is symmetric with respect to the origin. The reciprocal function. So you put in x, you get 1 over x, which is the reciprocal of whatever x is. So if you put in 2, you get 1 over 2, 1/2. If the number you put in for x is 1/2, then what you get out is 1 over 1/2, the reciprocal of 1/2, which is 2. If you put in 3/5, the reciprocal of 3 over 5 is 5 over 3. The reciprocal of a negative number would be negative. So like the reciprocal of negative 4 would be negative 1/4. And if you try to put in 0, so you're taking 1 over 0, the reciprocal of 0, that's undefined. You can't do that with 0. So the domain of this function is all real numbers except 0. X can be anything less than 0, it can be anything greater than 0, but it can't be 0. And the range turns out to be all real numbers except 0. So what you get out of this function is the value of 1 over x. Could be any negative number, it could be any positive number, but it can never equal 0. And this is an odd function. Notice the graph is symmetric with respect to the origin, and it's in 2 separate parts. There's no point on the graph with an x coordinate of exactly 0, but there are points over here on this part of the graph with x coordinates that are negative and points on this part of the graph where x coordinates are positive. And on both of these parts, this is a decreasing function. So like as long as we just stick with positive or just stick with negative x's, the bigger x gets, the smaller 1 over x gets. Now here we have the greatest integer function. This is one of those things that it's real simple once you see what it does. It might take a minute to get the hang of what's actually going on here, but once you see it, it's easy. This is the function that takes whatever number you give it and rounds down to the greatest integer that is less than or equal to the number you put in for x. That means if the number you put in is already an integer, if it's already a positive or negative whole number, then you just get that same number. But if what you put in is not already an integer, like if it has something after the decimal point, this function will round down to the nearest whole number or nearest integer. So for example, f of 1.896 comes out to be 1. Actually, f of 1 point anything would come out to be 1. Notice on the graph, all the points with x coordinates between 1 and 2 have y coordinates that are exactly 1. So you got where x is 1 and y is 1. You got where x is 1.3 and y is 1. You got where x is 1.896 and y is 1. You got where x is 1.99, just a little bit less than 2, and y is 1. And then when you got to where x is 2 exactly, then y starts being 2. F of 3 is 3. F of pi, remember pi is that number that's approximately 3.14, but it's a little bit bigger than 3, so the greatest integer function would just round it down to 3. F of 1/2, well, if you start at 1/2 and go down until you hit an integer, the integer you hit is 0. F of negative 6.8, if you start at negative 6.8 and go down until you hit the next integer, what you hit is negative 7. To get to negative 6, we'd have to go up, but we go down and we hit negative 7. F of negative 42 would be negative 42. And this is an example of what's sometimes called a step function, because the graph just looks like a series of steps. It goes along being constant for a while, and then all of a sudden it steps up to the next level, and then the next, and then the next. And our book uses the fairly common notation of these double square brackets around a number to indicate that function, the greatest integer less than or equal to that number. But other books and graphing calculators and apps and things like that I've seen spell it out as int of x, or they use these sort of half square brackets with lines on the bottom but not on the top. So it gives you something that's below the number you put in for x. Okay, one thing we have left to talk about in this section is piecewise defined functions. That's not going to take real long, but this video is already starting to run a little long, so I'm going to end this one here and come back in another one, and we'll wrap things up talking about piecewise defined functions.